Start with Robert Brandenburger from McGill University, who's going to tell us about emergent metric spacetime from matrix theory.
Great. So can you hear me well?
Yes, perfectly.
Okay, good. So I would like to thank the organizers, in particular Ghazal, for inviting me to speak. And I realize that the audience is a combination of mathematicians and physicists. Now, I'm really excited to talk about this particular research avenue, emergent metric spacetime for matrix theory. This is collaborative work with Shudo Brahma, who's now a fellow at University of Edinburgh, and with my excellent student Samuel Laliberté at McGill. Now, the reason I'm particularly excited to talk about this in this audience is that we need help from mathematicians to really make sense, mathematical sense of what I'm going to present to you. So let me start with some motivation. There's first of all motivation for mathematicians. So to put the work into context. So a long-standing dream of theoretical physics has been to obtain a unified quantum theory of space, time, and matter. And this is a unified theory of all four forces of nature. And right now, superstring theory is the best candidate for such a theory. However, the problem is that we only have a perturbative formulation of superstring theory. So what I write here is the problem, only a perturbative superstring theory exists. And I put exists in quotation marks because I think mathematicians would not agree that this is really existence in a mathematical sense. Now, what I'm going to do today is to work with a matrix model, which is well-defined, and hopefully mathematicians will agree that this is a well-defined model. And this was postulated in 1996 as a non-perturbative definition of superstring theory. BFSS stands for Banks, Fischler, Schenker, and Susskind, the four physicists who proposed it. So this BFSS model is a theory of n by n Hermitian matrices. And in the limit where n goes to infinity, then we are supposed to get superstring theory. So superstring theory is conjectured to emerge in the n going to infinity limit of this model. Now, general relativists and cosmologists will realize that there's no space in this model. There's time, but no space. Now, this is bad, there's no space. However, the good thing is that there are no singularities. For example, there's no Big Bang singularity. So if we can make sense of this BFSS matrix model, there will automatically be no cosmological singularities. Now, there's no metric, there's no continuous differential geometry, and there's no gravity, which is bad for physics. And if this matrix model is a correct theory of the universe, then space, metric, and gravity must all emerge. And it is in this emergence where we will need some help from mathematicians. So this is the two motivational slides for mathematicians. And now
Robert, can I ask you a question?
Yeah, go ahead.
Should it be really clear that time is present here?
Yes, and you will see that we have a Lagrangian, and the action is an integral over time of the Lagrangian. So I will present to you the action, and in the action there is a time variable. Now you see the time variable is a mathematical time variable, and it will not be the physical time, but there's a temporal variable. So are you happy with the answer?
Yes, thanks.
Okay. Good, so these were the two motivational sides for mathematicians. Now will come a motivational / provocative slide for cosmologists and for physicists. So all cosmologists and physicists know that the inflationary scenario is the current paradigm for early universe cosmology. And inflation is usually analyzed using an effective field theory framework. And I will define a little bit later what I mean by effective field theory. However, I will argue that there are fundamental conceptual problems applying effective field theory to situations where you have a rapidly expanding universe. And these are not just small problems, they are problems of unitarity and inconsistency with the second law of thermodynamics. So I'll try to persuade physicists of that problem. And then if you accept that, then you will have to agree that we will need to look beyond an effective field theory description if we want to understand the early universe. And this brings me back to this matrix theory cosmology, which is an attempt to start with a non-effective field theory description and to try to get gravity out of it. Okay, so here's the outline. I will first argue that we really need to go beyond effective field theory if we want to understand the early universe. This is a Trans-Planckian censorship discussion. And then I will try to persuade cosmologists that in order to obtain a successful early universe cosmology, there is more than one scenario in the market, not just inflation. So then I will turn to the main point to both mathematicians and physicists, and this is this particular model, the emergent metric spacetime from matrix theory, and the cosmology that follows from that. And mathematicians will probably be shocked at the lack of rigor in the discussion that I will give. And, but hopefully I'll persuade physicists that this is a promising avenue. So this is the outline for this morning's talk. So let me start with the Trans-Planckian censorship discussion. So here, on the top of this slide, you see a space-time sketch. So the vertical axis is time, the horizontal axis is physical spatial distance, and this space-time diagram corresponds to an inflationary universe, where the universe begins with a Big Bang singularity at 0, and then there's a finite duration between T sub I and T sub R, between these two times, when space expands exponentially. This is inflation. And after time T sub R, then standard Big Bang cosmology takes over. So this is a timeline of inflationary cosmology. And in this diagram, I sketch different length scales. So the first length scale, which I will map out with my cursor, this is the horizon. And by the horizon, I mean the forward light cone of a point at the initial Cauchy surface, which I take very close to time t equals 0. And as space expands, the distance that light travels expands. And when space expands exponentially, the distance that light travels also expands exponentially. So the horizon increases exponentially during the period of inflation. Now, the second length scale, which I plot, is the so-called Hubble radius, which is the inverse expansion rate of space. And if space expands exponentially, then the rate of expansion is constant and the Hubble radius is constant. So you see that during this phase of inflation, there's an exponentially growing difference between horizon and Hubble radius. Now, the third length scale, which I plot, is the physical length, which corresponds to scales that we observe in cosmological observations. So observers look at the sky, and they look at the microwave background, and they see anisotropies in the microwave background, small amplitude anisotropies. Or you look through optical telescopes, and you see the distribution of galaxies, and on large scales, the galaxies are not so non-randomly distributed, but they are non-randomly distributed. And the way that we describe the structures, like small amplitude plane wave inhomogeneities superimposed on the expanding background. And the length scale of this inhomogeneities expands in proportion to the size of space. So during the period when space expands exponentially, the wavelength of inhomogeneities also expands exponentially. And so in this inflationary universe model, if you go far enough back in time, and if this phase of inflation lasts long enough, then all scales that we observe today start out with a length scale smaller than the Planck length. And now this should give rise to a red flag to all gravity experts. Namely, it is clear that we do not understand physics on length scales smaller than a Planck length or the string length. So in this inflationary scenario, stuff that we observe today all starts out in this zone of ignorance. And so therefore, 20 years ago, Jérôme Martin and myself argued that in order to understand the evolution of structure in the universe, to understand what we see with telescopes, we need that effective field theory breaks down, and we need a new paradigm. Now, based on this discussion, 3 years ago, Bedroya and Waffa made the following conjecture. They postulated that in no model consistent with a complete physical theory, so here I'm making a distinction between model and theory, so no model consistent with, coming from a consistent physical theory, can have the feature that initial Trans-Planckian modes ever become larger than the Hubble horizon. Mathematically, this means the following. If we take the metric of space-time to be described in this way, homogeneous and isotropic metric, t is time, x, these x's are the coordinates which are painted onto the expanding background, and a of t describes the size of the spatial sections. A of t is the scale factor. H of t is the expansion rate. The Hubble horizon is the inverse of that. And so this Trans-Planckian censorship conjecture mathematically means what I have in a box. Namely, you start at any initial time t sub I with the Planck length, you evolve to any later time t sub r, and you have to remain smaller than the Hubble horizon at this later time t sub r. This is the mathematical formulation of the Trans-Planckian censorship conjecture. Now, how could you motivate this conjecture? And I will give you 3 motivations. The first one is in analogy with Penrose's black hole censorship hypothesis. So here I plot a sketch of a black hole with charge q smaller than the mass. So r is the distance from the center of the black hole. Here's the center of the black hole, the singularity. Here is an observer far away from the black hole. And according to the Einstein equations, if you have a black hole with charge smaller than a mass, then the observer far away from the black hole is shielded from the bad stuff that happens at the singularity by a horizon. So no information can reach the observer from this bad region. Now, Einstein's equations admit solutions with charge greater than a mass. And for those solutions, the observer far away from the black hole would not be shielded from the singularity. This is a physically pathological solution. And so Penrose conjectured that in no consistent theory that completes general relativity, you can have such solutions. So these type of pathological solutions should be prohibited. So the external observer should be shielded from the singularity and from the non-unitarity by a horizon. So now we will translate this to cosmology. Position space becomes momentum space. The singularity becomes wavelength smaller than a Planck length. The black hole horizon becomes the Hubble horizon. And then Penrose, translated to cosmology, says that the observer, who's measuring only long wavelength modes, must be shielded from the short wavelength modes. Trans-Planckian censorship conjecture. So the second justification for the Trans-Planckian censorship conjecture is unitarity of the effective field theory. So what do we do in effective field theory? And so mathematicians should be shocked by that. But we do the following. We take all the fields that we have, classical fields, we expand these fields in Fourier modes And these are Fourier modes in the x coordinates, the coordinates which expand as space expands, co-moving coordinates. So for each co-moving wave number, we have a Fourier mode, and we quantize each Fourier mode as a harmonic oscillator, as I think even all mathematicians learn in the basic quantum mechanics, first course in quantum mechanics. Now, in order to avoid the famous Planck catastrophe, you have to impose an ultraviolet cutoff. You can't have wave numbers and energies which are larger than the Planck wave number or Planck energy. But these co-moving, these modes are co-moving, and the cutoff has to be at a fixed physical scale. And so to maintain the fixed physical scale in an expanding universe, you have to continuously create new modes. And this is non-unitarity. Your Hilbert space is growing as a function of time. Now, if you demand that this bad stuff, this non-unitarity, is hidden from the observer who only measures super Hubble modes, then you get precisely the Trans-Planckian censorship conjecture. Okay, now there's the famous cosmological constant problem, which is also associated with effective field theory. So again, in effective field theory, you expand all fields in co-moving Fourier modes. You quantize each field as a harmonic oscillator. Each harmonic oscillator is ground state energy. Each ground state energy acts like a contribution to the cosmological constant. You add up all ground state energies and you get something enormously large, 120 orders of magnitude, larger than what is acceptable. So this is a usual view of this famous cosmological constant problem. And I claim that this is an artifact of doing this bad analogy, a bad analysis. It's an artifact of expanding matter fields in Fourier modes using effective field theory. And if you have a different starting point, the cosmological constant problem will have a very different light. Okay, the third justification is an entropy justification, and I'll be brief on that. So physicists these days talk a lot about entanglement entropy density. In the case of black holes, it's entanglement entropy between stuff inside the horizon, outside the horizon. We can do the same thing in cosmology. We can look at entanglement between modes which are super Hubble and sub Hubble. And if we have an accelerating background, then the phase space of super Hubble modes grows. Therefore, the entanglement entropy density grows. And if we demand that the entropy density remains smaller than the entropy density that we want at the beginning of the Big Bang phase, we get exactly the Trans-Planckian censorship conjecture. So bottom line is that if you work with effective field theories in cosmology, you are in danger of doing something which violates the second law of thermodynamics and is non-unitary. Okay, I will skip this. So this is bad news for inflationary models, and it also tells us that dark energy, the thing that we know absolutely nothing about, except that it contributes 70% of the present energy density of the universe, this mysterious stuff cannot be a cosmological constant. Okay, now, so scenarios for successful early universe cosmology. So we want to explain the data. And here is one piece of data. So we look at the sky, we measure the microwave background radiation, and the microwave background radiation is not completely isotropic. So we can measure the small amplitude anisotropies on different angular scales. So on the horizontal axis is angular scale. On the vertical axis is the strength of the anisotropies on the corresponding angular scale. And these black dots with the error bars, that's the data from the WMAP satellite. You see statistical error bars and some systematic uncertainties. And this red curve is a nice curve that fits the data fairly well. And to get this data, well, who predicted this nice curve? This curve was predicted 10 years before the discovery of inflationary cosmology. It was predicted by Zeldovich and Zuniaev and by Peebles and Newton. And here is a demonstration from the Zuniaev-Zeldovich paper of 1970. This is time, the vertical axis, the horizontal axis is space, these co-moving coordinates. And Zeldovich and Zuniaev argued the following. They said, let's assume that the universe starts out with plane wave perturbations on all scales. Now, if you study small amplitude inhomogeneities in an expanding universe, you find that for wavelengths larger than this length scale, which is the diagonal line here, which is the Hubble rate before the time of recombination, when the microwave background is produced, that on these large scales, the perturbations are standing waves that don't oscillate. But as soon as the wavelength enters the Hubble radius, the waves start to oscillate. So the wave that enters the Hubble radius right when the microwave background is produced has had no time to oscillate. We catch it at maximal amplitude. The wave that has done 5/4 of an oscillation, we catch it at the minimum, and so forth. And so based on this picture, which was discussed in 1970, 10 years before the development of inflation, this curve was predicted. This is the angular scale that corresponds to lengths that enter the Hubble radius right at recombination. So this is what I say, the acoustic oscillations in the cosmic microwave background, angular power spectrum, and also the oscillations in the matter power spectrum were all predicted 10 years before inflation. Now, for successful early universe cosmology, you need isotropy of the microwave background on large scales. And for that, you need the horizon to be much, much bigger than this Hubble radius. You need scales that we observe today to originate inside the Hubble radius. Otherwise, we can't causally predict the origin of these fluctuations. Zeldovich and Zuniaev did not predict the origin of these fluctuations. They just said, given fluctuations, we will get these predictions. And finally, we need a third point. Inflation is one way to realize all these three conditions, because the horizon becomes exponentially larger than the Hubble radius. Scales that we observe today start out with a wavelength smaller than the Hubble radius, and the third criterion is also satisfied. But if you have a bouncing cosmology, and Ghazal is working a lot on bouncing cosmologies, you can also realize these three conditions, because in bouncing cosmologies, time runs from minus infinity to plus infinity. This is a bounce point. And scales that we observe today, they start out smaller than the Hubble radius. If you go back sufficiently back into the past. And in certain bouncing models, you can also satisfy the third condition. Now, the scenario which will become important at the end of my talk is the emergent scenario, where we assume that there's a phase in the universe which looks like it is quasi-static. And then there's a phase transition to the usual expanding phase of standard Big Bang cosmology. So this is the assumption that's put in. This is a resulting space-time diagram, time, space. Time runs from minus infinity to plus infinity. So therefore, the horizon is infinite. Criterion 1 satisfied. The Hubble radius in the quasi-static phase, static means h equals 0, Hubble radius infinite. Scales are sub-Hubble at early times. Criterion 2 satisfied. And as I will show you, there is a mechanism to also satisfy criterion 3, the scale invariance of the spectrum. So bottom line, if some of the mathematicians got lost here, the bottom line is there's more than one early universe scenario which is consistent with data, not just the inflationary scenario. And of these three basic scenarios, bouncing cosmologies and emergent cosmologies are consistent with a Trans-Planckian censorship conjecture, whereas inflationary cosmologies, unless you tweak them, are not consistent. So bouncing cosmologies and emergent cosmologies have an advantage. This is meant to be a provocative comment to cosmologists. But in all scenarios, you have to go beyond effective field theory to really understand what is going on. And so with that, I will now turn to our proposal for an emergent space-time and emergent early universe cosmology from a non-productive starting point. And here is the point where mathematicians should start to become shocked, because this is where we need their help. Okay, so we are starting with a matrix model. So we have 10 n by n Hermitian matrices, and n will go to infinity. And as I said before, this matrix model was proposed because in the n going to infinity limit, it is a possible non-productive definition of superstring theory. This is the Lagrangian. So xi, these are 9 n by n Hermitian matrices. There's the commutator of the matrices, square. This looks like a potential energy term. This looks like a derivative term, covariant derivative term. So this d sub t involves partial derivative with respect to time. So these xi's are functions of a time. And this d sub t has two terms. One term is partial derivative with respect to time. And the second term is a commutator with a 10th matrix a sub 0. Now there's also a coupling constant, g square, in the matrix in this Lagrangian. And the limit, n going to infinity limit, which we are taking, involves keeping this lambda, g square n, constant. So this is the definition of this matrix model. So, okay, so we have a Lagrangian, we have an action, and we will pick a state. We will take this matrix model to be in a high temperature state. Now, in a high temperature state, it's an equilibrium state, there's no time evolution. Okay, now we will take a high temperature state, and what we can do now is we can expand these matrices in a Fourier series in Euclidean temporal direction. This is this expansion. This is called the Matsubara expansion. And at high temperatures, it turns out that it is the zero modes, the n equals 0 modes, which dominate the action. And the action is the integral of the Lagrangian. So this is what you have. And the IKKT action is this action. So now we have 10 n by n matrices. We have no time, no space. All we have is an action and a partition function. And this partition function involves a function integral over all of these matrices with the canonical measure. And then you see there are also fermionic variables, because this is a supersymmetric matrix model. And there's also the corresponding measure for the fermionic variables. So this is the definition of this IKKT matrix model. No space and no time. Now, these are Hermitian matrices, so we can diagonalize one of them. And we will choose to diagonalize a sub 0. And we will identify the eigenvalues of a sub 0, so the diagonal elements of a sub 0, as the emergent time. Now, numerical studies show that in the n going to infinity limit, the trace of a naught square, the expectation value of that, scales as kappa times capital N, where kappa is a small constant. And that implies that the maximal eigenvalue scales as square root of capital N, and therefore the difference between eigenvalues scales as 1 over square root of n. So you see in the n going to infinity limit, we therefore get infinite continuous time. And these eigenvalues are symmetric about 0. So the time that emerges is time that runs from minus infinity to plus infinity. not from 0 to infinity. So there's obviously going to be no Big Bang singularity in the cosmology that emerges. Okay, so this is our emergent time. So now let's look at these spatial matrices in the basis in which A0 is diagonal. So now by looking at the action and applying the Riemann-Lebesgue lemma, you can show that if you go away from the diagonal, then the expectation values of the spatial matrix elements, so the expectation value of the spatial AI square, decay if you go sufficiently far away from the diagonal. And sufficiently far means n sub c greater than something that is proportional to square root of capital N. So this third line and the fifth line, we have some analytical understanding of that. Now there's numerical evidence that if you are less than n sub c away from the diagonal, that then these quantities are approximately constant. Okay, so now let's do the following. So we want to get emergent space and an emergent metric. So we work in a basis in which A0 is diagonal. And we will take a particular time, which means a particular distance down the diagonal. And at that time, we will look at submatrices of the spatial matrices, which are positioned at a distance t down the diagonal, the distance corresponding to here. And we will take small n by small n submatrices. So this is what we do. And then for these small n by small n submatrices, AI bar, positioned at a time t, we can define the extent of space parameter in this way. So I is the ith spatial dimension. There are 9 spatial dimensions. Okay, so we can, and we are not the first to do that. Now it's been observed that there's a spontaneous symmetry breaking. The SO9 symmetry of the Lagrangian is broken by this finite temperature state into SO6 cross SO3, in the sense that only 3 of these extent of space parameters become large, and the other ones remain small, Planck size. So this means that we automatically get 3 large dimensions of space. Okay. Good. So we continued this analysis, and we now propose to identify the integer n sub I, so the length scale of these submatrices, the I submatrix. We will identify that with the ith co-moving coordinate. And the physical distance of a curve along the ith coordinate axis between ni equals 0 and ni, this length is given by this quantity. So this is the generalization of the extent of space parameter. So this is physical length defined this way, or co-moving coordinates are defined this way. And if we have length and co-moving coordinates, then we can construct the metric as we do in differential geometry. So G, the II component of the metric, is given by the derivative with respect to ni of this length. Okay, so this is the proposal for emergent space and an emergent metric. Okay, so now we use the fact of these matrices for which we do not yet have a good analytical understanding, this fourth point, we use that. And from here, it follows that the metric is independent of n sub I, for n sub I smaller than n sub c. We use SO3 symmetry, And that gives us this spatial metric. And this spatial metric is a homogeneous metric, spatially flat. So if this proposal of emergent space, an emergent spatial metric makes sense, then we will automatically get a spatially flat, infinite space emerging. Infinite because n sub c goes to infinity as n goes to infinity. So this is our proposal of emergent space, emergent time, and emergent metric from this matrix model. And now I don't think I have much time. I think I have maybe 4 minutes. So I have only one more section to discuss, and I'll be a bit brief on that. This is a cosmology. So first of all—
Robert, you have 10 more minutes.
10 more minutes, but I want to leave time for questions.
Sure.
So if you solve the classical matrix equations in the large, for the subspace, which becomes large, you solve the classical matrix equations, then you find that the scale factor grows as t to the 1/2, like that of radiation. There's no sign of a cosmological constant. So the space-time that emerges from this proposal has no cosmological constant. And there should be. There's no reason why there should be a cosmological constant, because we are never quantizing a harmonic oscillator. We're starting with a matrix model. We are quantizing the matrix model. There are never any harmonic oscillator ground state energies. So the cosmological constant problem is simply not present in this approach. Okay. So the Japanese group of Nishimura et al., who've worked on these matrix models for 20 years, they've mostly studied the IKKT model. And recently we've shown that the phase transition also occurs in this BFSS matrix model, the model that we are considering. So we've shown that there is a symmetry break in phase transition, but we have not been able to show that this is the final state that emerges after the symmetry breaking. Although I have good physical reason to expect that also in the BFSS model, this is the state that minimizes the free energy after the symmetry breaking. Okay, so now we have a thermal system. We have this matrix model at finite temperature. Now, in any finite temperature system, there are thermal fluctuations. And we now postulate that it is the thermal fluctuations of this matrix model that give rise to the curvature perturbations and gravitational waves, which we observe today in the universe. So I think you should all agree that in a thermal system, there are thermal fluctuations. And if the early universe is a thermal system, then vacuum fluctuations are not important. It is thermal fluctuations that should be important. Okay, so this should be quite obvious. And there's a clear way to find the curvature perturbations and the gravitational waves by computing matter correlation functions in this thermal state. Okay, so the way that we do the calculations is we compute the matter correlation functions like the energy density fluctuations, the pressure fluctuations in this emergent phase from the finite temperature partition function. And then for each wavelength, we convert the matter fluctuations to space-time fluctuations at the time when the physical wavelength becomes equal to the Hubble radius. So that's during the transition between the emergent phase and the standard Big Bang phase of expansion. So this is the way that we do the calculations. So I pause here just so you can see the method. So all these matter correlation functions are given by the partition function of this matrix theory, the finite temperature partition function of the matrix theory. This is standard statistical mechanics. And the way that we correlate matter perturbations, energy density perturbations, and off-diagonal pressure perturbations, here you should add I not equal to J. the way we correlate them to curvature perturbations and gravitational waves, which enter into the metric in this way, is by these two equations, which are the Einstein constraint equations for linearized cosmological perturbations. So our method is that we take the partition function of our thermal system, we compute these two quantities, and then we infer what the curvature perturbations and the gravitational waves are. So you see what we are doing. We have this matrix model, no space and no time. We've argued that we get an emergent cosmology from that, and we are going to compute things that can be measured in cosmological observations. Okay, so this is the power spectrum of curvature perturbations. The power spectrum is defined this way in terms of Fourier modes. It's a root mean square fluctuation of this phi in a ball of radius k inverse. This is given by the specific heat capacity. The specific heat capacity is given in terms of the temperature derivative of the finite temperature internal energy. The internal energy is given in terms of the inverse temperature derivative of the logarithm of the partition function. So given the partition function, we can calculate all of the matter correlation functions. And what we find is that the curvature perturbations are scale invariant, which is what is observed, with a Poisson contribution on very short wavelengths. And the gravitational waves also have a scale invariant power spectrum. And I'm not showing you the details, you can ask me later. So what do we have? We are starting with a matrix model. There's no space. We take this matrix model in a finite temperature state. So we've eliminated the time evolution. From this matrix model in a finite temperature state, we get emergent infinite time, emergent infinite space, an emergent spatially flat metric, and we get thermal fluctuations which are completely consistent with what is observed today. Okay, now there are a large number of problems, open problems for cosmologists like myself. So far, we've only considered the bosonic matrices. We haven't considered really the fermionic, the Grassmann variables. Also, we need to understand the phase transition between the emergent phase and the expanding phase better. When and how does a classical analysis of the three large dimensions become valid? And then you see we need the help of the mathematicians once we get to this question. We need, does general relativity emerge in the infrared? Is there a differential geometry that emerges in the infrared? Going back to cosmologists, we would like to calculate the small deviations from scale invariance. We would like to understand dark energy, and we would like to obtain the low energy effective field theory, all from this matrix model. So what we've done so far is just pointed out a new research direction, which I'm very excited about, but it's obviously, it could all be wrong. Warning. So now, open problems for mathematicians. This is what geometrical structures emerge from this discrete model in the n going to infinity limit? Is there an emergent differentiable manifold structure? Are there mathematically well-defined analogs of metric connection for finite n? So it's here we would appreciate lots of help. Okay, so let me conclude. I have a couple of concluding slides. This is a concluding slide for cosmologists. Inflation is not the only scenario of early universe cosmology consistent with current data, even though that belief has made it into basic astronomy texts. Now, in light of the Trans-Planckian censorship conjecture and other conceptual problems, effective field theory models of inflation are really not viable. If you want inflation, you have to go beyond effective field theory. And if you really want to understand the early universe, you have to go beyond effective point particle field theory. So these are conclusions for cosmologists. More general conclusions are that we've presented a matrix model, the BFSS matrix model. It is a proposal for non-perturbative definition of superstring theory. We've taken this matrix model in a high temperature state, and we've indicated a way in which we might be able to get emergent time, emergent space, and an emergent metric. And if this works, then the emergent time will be infinite in both directions. The emergent space will be infinite from the beginning, and the emergent metric might be spatially flat. And then we've computed thermal fluctuations in this matrix model, and we show that these thermal fluctuations are in good agreement with the current data. And we would like to extend this and compute small deviations from scale invariance with which we might be able to make distinctive predictions. There is no cosmological constant in this model. Okay, so thanks for listening.
Okay, let's open the floor for questions. Let's start with the audience person.
Hi, Robert. Thank you for the nice talk. I have 3 questions, but if there are more questions, I can stop. The first one is for your, let me understand this. When you quantize the matrix, first of all, is the temperature another fluid plus the action of the metric, or is it within the same matrix action?
It's within the same matrix. So you see, if you have a Lagrangian, then you always have to specify a state. So this is a state of the matrices.
Okay, so is it the thermal fluctuation around that state? Am I understanding this correctly?
It's fluctuations of the matrices around their mean value. Around the expectation value. So you see, space, time, and matter will all come out of the matrices. Most of the matter will come from the fermionic matrices, which I didn't write down here, but I wrote them down in this slide.
Okay, and can you give me an intuitive way to see when then you do the quantization, they don't have their own ground state, so they don't contribute to cosmic CC problem, or?
See, we are not quantizing harmonic oscillators. In condensed matter systems, there is never a cosmological constant problem.
I see. And now if I'm thinking ahead, and you mentioned that's an open problem with the low energy, if I'm thinking, okay, I solved the original CC, but if I have during, I don't know, electroweak transitions or other standard particles production, even the quantization at that level, there is no ground state contribution, or it's still coming out?
No, there will not be. There will be temporary potential energy of the matter fields.
So is it that we have to rethink all the standard model of particle physics?
No, not at all. Not at all. See, the standard model of particle physics all the standard model fermions will come from the psi alphas. And even some of the gauge fields will come from it. And then there are also some of the scalar fields and maybe gauge fields will also arise from these sub A matrices, which do not correspond to the 3 large dimensions.
Okay. Yeah, I see. Thank you. I appreciate it.
Hi, Robert. So I wanted to ask about, you mentioned this open question about does general relativity emerge from this in the infrared limit? On the other hand, you also showed us a slide where you said, here is the space-time metric emerging. So what, beyond the space-time metric, what does it mean? Does general relativity emerge from this?
Okay, so by that I
slide
mean
40. Slide 40.
Yes. Okay, thanks for being so. Okay, so you see, I would like to see gravity emerging as a force between localized excitations in the matrices. So if you have two clumps of matter, and the matter will be these excitations of fermions, how will they interact? So it's basically, if you just have a differentiable manifold, Bastido remind you differentiable manifold, you don't yet have Einstein gravity. You need a specific action. And what that action does is that action tells you how matter particles interact.
Thanks.
I also have a question on this page. You're recovering the metric tensor here. Are you only recovering a space-like part of it, or are you is the causal
Yes,
structure?
very good question. Yes. So you see I'm only, first of all, on this slide, I'm only recovering the GII components for I equals 1, 2, and 3. Not even yet the GIJ components. And then I use the symmetry assumption, the symmetry result, and then I get the GIJs, but I only get the spatial one. And then what I will argue is I will argue that this represents the metric in synchronous coordinates. And in synchronous coordinates, the G0I will vanish. And the G00 is 1. But you see, this is all words. I'm arguing this. This all ought to be better presented. Or maybe it's wrong. But this is the way. So the only thing that I have a good, the last equation on this slide, I think this makes sense. And then the rest is sort of all educated physicists' guesses.
I see.
Everything
Okay.
else here.
Okay, maybe one last question before the break.
So, Professor Brandenburger, thank you for your talk. I'm a mathematician and I would like to help, but I have a concern. And my concern is in this 50 minutes, you have given us enough homework that if you start working now, we may be done in 10 to 20 years. And my concern is once we answer all these questions and we come back, what guarantee do we have that you guys have not meanwhile moved on to something yet completely different and unimaginable at this point?
Well, you see, I think you should set yourself a small side problem. Make something a little bit more rigorous. Also, so what you mentioned is a good concern. I have in the past collaborated with mathematicians, in fact, mathematicians who have connections with the Fields Institute, and we have been able to do interesting collaborative work. So if you have good ideas, please contact me.
Okay, thanks.
Okay, thank you very much, Robert.
So thanks again to all of you, and I apologize not being able to be with you in person. So I'll stop sharing the screen.
Now I think we have about 20 minutes for coffee.
Can I ask you another question since I'm online
Sure.
also?
Sure.
So I'm Christina, from one of the organizers.
Yep.
I'm a mathematician. I'm a geometer though, so I'm very interested in this discrete process becoming continuous. Your time is stretching out automatically as part of this limit.
Yes.
Yeah, so that's very interesting. Is it ever possible you would imagine that 2 times might have stretched out?
Sorry, can you repeat the last?
That why is it that you get a clear single direction of time out of your theory?
That's a good question. So this has to do with fluctuations. So if you have a time symmetric background and you pick an initial state, then the fluctuations will grow in amplitude in one direction.
Mhm.
So it's see, the fluctuations always have a growing mode. And that means that space deviates from being homogeneous. So you put in a low entropy state, and the entropy will be growing.
Okay. So your entropy is kicking off time, which makes sense.
Right.
Okay, cool. Thank you.